Approximately 1 to 2% of the global population is on the autism spectrum. For decades, diagnosis has depended on clinicians trying to identify these subtle behavioral patterns through subjective observation alone. This reliance on a small pool of specialists has created a massive medical bottleneck. In many regions, waitlists for a formal evaluation exceed a full year. This delay has a measurable biological cost. The most intense period of neuroplasticity, the brain's peak ability to adapt, occurs before age 3. Every month spent on a waitlist is time lost during that developmental peak. Standard observation often fails because autism is highly heterogeneous. It presents as a collection of individualized signs that can easily evade the human eye during a brief clinical session. Artificial intelligence offers a way to quantify these behaviors by tracking digital biomarkers. These are objective, measurable data points, like gaze duration or vocal frequency, that provide a consistent baseline for detection. Shifting from delayed, subjective opinions to real-time, objective data is the most direct path to securing the window for early pediatric intervention. The first layer of this computational mapping uses computer vision to analyze external behavioral data. This chart displays how eye-tracking algorithms identify specific ASD tendencies. While typically developing children prioritize faces, these points show a distinct preference for geometric information. Simultaneously, during tablet play, the system records secondary data, like blink rates and the hand's erratic motor micromovements. The analysis moves from the observable surface to the internal biological substrate, using neuroimaging to map the brain itself. Deep learning models can process fMRI scans to identify altered connectivity within the default mode network, a region essential for social cognition and executive function. These models also quantify structural differences, such as reduced white matter integrity in the tracks that facilitate communication between brain regions. Behavioral tracking and brain imaging each provide distinct indicators, but assessing them as isolated variables fails to capture the holistic complexity of the disorder. The breakthrough for capturing that complexity is a process called Multimodal Fusion. This is a representation of deep neural networks ingesting and seamlessly merging entirely distinct categories of data at the same time. The AI cross-references eye-tracking data with internal EEG brainwaves and historical medical records. This fusion allows the system to identify hierarchical representations, hidden correlations between data types that would otherwise appear unrelated. These multidimensional patterns are mathematically too complex for human cognition to synthesize at once. A machine can process thousands of these intersections in seconds. Multimodal fusion acts as a high-definition lens, finally mapping the heterogeneous landscape of autism into a unified diagnostic profile. This technology is moving out of the lab and into the clinical environment. Regulatory bodies like the FDA have authorized the first AI diagnostic aids, specifically to help primary care physicians identify signs of autism in young children. This helps democratize access to screening, bypassing specialized waitlists and enabling objective assessments in a child's home or primary care office. However, medical adoption faces an ethical hurdle, the black box problem. Doctors cannot prescribe treatments based on a machine's output if they don't understand the logic behind it. This diagram shows how Explainable AI, or XAI, solves this by forcing the algorithm to highlight the exact features that led to its conclusion. It links specific eye gaze metrics directly to EEG frequencies to explain the output. This transparency is essential for building trust. It allows the pediatric community to verify the evidence and ensures algorithmic fairness across different populations. AI provides the objective quantification that subjective observation lacks. This evidence gives doctors the definitive proof required to initiate early intervention and improve a child's developmental trajectory.